Hello. In this lecture, we will discuss about the order of convergence and Newton's method. What is order of convergence? Let Xn be a sequence of approximation, that converges to alpha. Alpha is the real root. Okay. Then the order of convergence mainly describes the speed of convergence. That means what? With how much speed the sequence is converging to the exact root alpha. Let us suppose the sequence 1 upon n is given to you, and 1 by 2, 1 by 3 and so on. It is converging to alpha. So alpha is what? That is 0. 1 upon n square, that is 1, 1 by 4, 1 by 9 and so on. This is also converging to 0. Then the order of convergence of 1 by n square is more. Why it is more than the 1 upon n, as if we will see after 50 steps, as we can see after 50 terms, we can say after 15 terms, what will be the value of 1 upon n? 1 upon n will be what? After 50 steps, 1 by 50, and 1 upon n square will be what? That is 25, 1 upon 2500. Okay, so what does it imply? That 1 upon n square is, that means 1 upon 2500 is more closer to 0 as compared to 1 upon n, that is 1 upon 50. So which will converge faster? 1 upon n square will converge faster. Okay. So out of these sequence 1 upon n and 1 upon n square, the speed of convergence of 1 upon n square is faster than the 1 upon n. Now write the definition of convergence, order of convergence. Mainly the speed will depend on the order of convergence. What is order of convergence? So let us write the definition of order of convergence. Order of convergence. That means let Xn be a sequence converges to alpha, then Xn minus alpha, let us denote it by En. That is error between the Xn and alpha. So the difference between Xn and alpha is what? Let us represent it by En. And En plus 1, that means the error at the n plus 1th step. Then the sequence Xn plus 1 minus the term at the n plus 1th step is x, n plus 1 minus alpha. Then we can write limit n is tending to infinity, Xn plus 1 minus alpha upon Xn minus alpha raised to power p equal to limit n is tending to infinity En plus 1 upon En raised to power p equal to C, where C is a constant, any constant, and P is greater than equal to 1, that is the called order of convergence. Then P is called order of convergence, order of convergence of the sequence Xn. This C is called asymptotic error constant. C is called asymptotic error constant. Okay. When P equal to 1, then if we are taking the case when P equal to 1, what does it imply? That is En plus 1 upon En equal to C. In that case, En plus 1 equal to En. Okay. For P equal to 2, En plus 1 equal to En square. Let us check how the order of convergence affect the speed of the method. Okay. Now, if let us suppose whenever we are having P equal to 1, that means for the linear case, and we are assuming that the error at the 10th step is 0.002, then the error at the 11th step will be what? It will be C into 0.002. But in this case, when P equal to 2, then if the error at the 10th step is 0.002, then the error at the 11th step will be what? C 0.002 square. That is what? C 0.00004 into C. So if in the linear case the error is what? That is constant multiple of error at the previous step. And in the when the order of convergence is 2 or P is 2, in that case error at the next step will be square of the error at the previous step. So in that case, in this case, error is moving towards 0 faster than the linear case when P equal to 1. So the case when we are taking P equal to 2, so error is moving faster, so we are interested to reduce error between the exact root and approximate root. That means whenever Xn is converging to alpha, that means in that case error will be small. As error will be small, that means Xn will converge faster to the root alpha. So we are interested in higher order of convergence. Okay. So this implies that if this implies that if P is large, then error will be 0 faster. Error will reduce faster. This implies that sequence is what? Xn converge to alpha, that is exact root, faster. Xn converge to exact root alpha faster. So as a note, order of convergence plays an important role in the theory of any iterative procedure that is producing a convergent sequence to the exact solution. That means high order of convergence, means method converge faster, less number of steps required to achieve the desired accuracy. Now there is a note about the asymptotic constant. For p equal to 1, that is for the linear case, c, that is asymptotic constant, plays an important role and c should be less than 1. For the p greater than 1, c is not, or c is less important. Okay. Next is Newton's method. So we have discussed about the order of convergence. Order of convergence is large, then the method will be better than the other method. So now we are going to discuss Newton's method. In Newton's method we are getting quadratic order of convergence. That will show with some examples. Let us, what is Newton's method? Suppose that f belonging to C2 AB. That means f and f dash are continuous inside the interval AB. F belonging to C2, that means f and f dash are continuous inside the interval AB. Let x0 belonging to the interval AB, that is an initial approximation, to exact root alpha, such that f dash x0 is not equal to 0. Because x0 is the approximation to alpha, then f of x0 near to 0 but not exactly 0, because that we are taking as initial approximation. And alpha minus x0 is small. Then f of alpha can be written as f of x0 minus alpha. We can add or subtract x0 to alpha and So we can add and subtract x naught. So what we can write here, f of x naught plus alpha minus x naught. We can expand it by the Taylor series. Expand by Taylor series expansion about x naught. So what we are getting, f of alpha equal to f of x naught plus alpha minus x naught f dash alpha, not alpha, this is x naught, plus alpha minus x naught square upon factorial to f double dash. It should be x naught, but if we are truncating series after x naught, after second term or the term, then we can replace x naught by some number c, where c is lying between alpha and x naught. Okay, c is lying between x naught and alpha. Okay, alpha minus x naught is small, so alpha minus x naught square is also very, very small. Obviously, when a number is small, then its power is also very small. Now, so solving this equation for alpha, ignoring this term because of this reason. Okay, f of alpha equal to f of x naught plus alpha minus x naught f dash x naught. Solving for alpha and f of alpha equal to 0, as alpha is the real root, exact root. Okay, what is coming out to be? Now find f of x naught plus alpha minus x naught f dash x naught equal to 0. Then the value of alpha is coming out to be, from here, alpha value is coming out to be x naught minus f of x naught f dash x naught. Write it in iterative form. We are getting here x. This is what is the exact root. So we can say this alpha, we can say this is the next approximation. We can assume it like that. So we can generate a sequence xn by writing this formula into iterative form. So xn minus f of xn upon f dash xn, n equal to 0, 1, 2 and so on. So this is called Newton's method, or also Newton-Raphson method. Okay, so in order to compute the value of xi, we required an initial approximation as we did in the 6-point method. Next is graphical representation of Newton's method. Graphical representation. Suppose fx is a function fx is a function, and we have to compute the root of the function fx equal to 0. So this is the root of the function. Okay. So let us suppose an initial approximation, that is x0. You can find an initial approximation of the function fx, and we have to take alpha is the x0 is the initial approximation. So this point, what is the coordinate of this point? x0, f of x0. We will find out the tangent at the point x0. Find out tangent at the point x0. The tangent is crossing x-axis at some point, that is x1. Join this point x1 with the graph of the function. That is what the coordinate of this point x1 f of x1. Now we'll find out the tangent at the point x1 f x1. This tangent line is crossing x-axis at a point x2. We'll join this point x2 with the graph. We are getting coordinate of this point x2 fx2. We'll continue this process. We are getting tangent line at the point x2. We are getting, this is x3. We'll join this x3 point with the graph of the function. We'll get next approximation, that is x3 fx3. We'll continue this process. So we are moving toward the root alpha. This is x4. Okay, we'll join this with the graph. So we started some initial approximation x0, and then we join that point x0 with the graph. The coordinate of the point is what? x0 fx0 on the graph of the function, and we'll find out tangent line at the point x0 fx0. It will, wherever it will cross the x-axis, that will be the next approximation, that is x1. We'll again join this point x1 to the graph. We are getting the coordinate of the point x1 fx1, and we'll find out tangent. Wherever the tangent will cross the x-axis, that will be the next point of approximation. So this is the Newton's method. Continue this process, it will move toward the root alpha. So this is the Newton's method. How Newton's method works, that we explain with the help of this graph. So I can write in words, starting with initial approximation x0, the approximation x1 is the x-intercept of the tangent line to the graph of f at x0, f of x0. The approximation x2 is the x-intercept of the tangent line to the graph of f at x1 fx1 and so on. Okay, so this is the graphical representation of the Newton's method. Let's do some example based on Newton's method. Apply Newton's method to find the root of the equation x cube minus 3x plus 1 equal to 0 within 10 raised to the minus 4. Okay, so this is what f of x equal to 0. F of 0 is what? That is 0 minus 3 plus 1, that is what? 3 into 0, 1. Okay, whenever we have to apply Newton's method or any numerical technique, we are required some initial guess. How to compute initial guess? For that there is one procedure, intermediate value theorem. What we do, with the help of intermediate value theorem, we can compute the interval in which the root is lying. So the very first step in any iterative method to find the initial guess. So that's why what I'm doing, I'm just putting we start with f of 0. F of 0 is coming out to be positive. Then we'll compute f of 1. F of 1 is what? 1 minus 3 plus 1. It is coming out to be minus 1. Okay. So that means what? F of 0, f of 1 is less than 0. So there exists a root inside the interval 0, 1. So the root will belong to the interval 0 to 1. Now, since the Newton's method is what? Xn plus 1 equal to xn minus f of xn upon f dash xn. When n equal to 0, what we required? We required x1 equal to x0 minus f of x0 upon f dash x0. What is this x0? x0 is the initial approximation. As I told you, we are just finding the interval in which the root lying. After that, we have to choose x0. How to choose this x0? As we have discussed in fixed point method, we can choose x0 as any point inside the interval 0 to 1. We can take x0 as 0, x0 as 1, x0 as 0.1, x0 as 0.2. But best is what? Just take the midpoint of the interval 0 to 1. But you are free to choose any point inside the interval 0 to 1. So whenever we are taking x0 as 0.1, then what would be the value of x1? x1 we can compute with the help of the right hand side. x0 is known to as f of x0, that means the function equation, and f dash x0 we require derivative of the function. So f of x is what here? X cube minus 3x plus 1, and the derivative of the function is what? That is 3x square minus 3. Okay, so x1 will be what? x0 minus x naught cube minus 3x naught plus 1 upon 3x naught square minus 3. Okay, so it is coming out to be x0, this value will be what? It is coming out to be 2x naught cube minus 1 upon 3x naught square minus 3. Okay, you can check from here. 3x naught cube minus 3 x naught minus x naught cube plus 3x naught plus 1 upon, minus 1. Minus 1 upon 0. Okay, this is x1. Now x net equal to 0.5 with the value of x1. It is coming out to be 0.3333. Okay. Similarly, compute the value of x2 with the help of x1. that is the value 0.347224. So similarly x3 is coming out to be 0.347296. The value of x4 we can compute 347296. Okay, so you can write in tabular form and xn plus 1 minus xn. Okay, so the value is 0.5 we choose. At the first iteration the value is computed at 0.33 and the difference between these values coming out to be 0.16666. Okay, what is the epsilon given to you here? Epsilon 10 raised to power minus 4. So the second iteration value is coming out to be 0.347222. The value difference xn plus 1 minus xn is coming out to be 0. So the difference between these two terms 0.013889. Third iteration the value is 0.347296. The difference between these two terms 0.000074. So obviously the condition is satisfied here. 347296. This is 0. If we are taking this. So the root will be what? Root is 0.347296, where the condition is satisfied. So this is the Newton's method. Newton's method moves faster than the bisection method, fixed point method. Why it is so? Because its order of convergence is more than the bisection method and fixed point method. So accuracy of the solution depends on the number of iteration used and nature of the equation fx equal to 0. Okay, next one more example. Compute the root of the equation cos x minus 5x plus 1 equal to 0 with the help of Newton's method. Epsilon is given as 10 raised to power minus 4. Solution. Fx is what here? Cos x minus 5x plus 1. So we'll find out first interval in which the root is lying. We'll start from 0. F of 0 is what? Cos 0 minus 5, 0 plus 1 equal to 0. The value is positive. F of 1, it is coming out to be minus 3.4596. That is the negative value. F of 0, F of 1 less than 0. So root is belonging to the interval 0 to 1. Okay. So find out f dash x, that is what? Minus sin x minus 5. Just keep in mind, whenever we are applying Newton's method or any method or to the trigonometric function, then always fix your calculator on radians. Okay, so you have to compute all trigonometric function value in radians. Use radian to compute trigonometric function. Trigonometric function. So fix radian in your calculator and then start to do calculation. So x1 is what? x0 minus f of x0 upon f dash x0. F of x is cos x minus 5x plus 1. Obviously the derivative we have computed already, minus sin x minus 5. Okay, so x1 will be what? 0.5 minus cos of 0.5 minus 5 into 0.5 plus 1 upon minus sin 0.5 minus 5. The value is coming out to be 0.5 minus 0.622174. Whenever we are required to 4-digit accuracy, for that we'll take 2 extra digits in our calculation, 1, 2, 3, 4, 5, 6, 7. So we can take 2 extra digits in your calculation. Even you can take more, 5.479425. The value is coming out to be 0.5 minus 0.1135917 0.386408. Now compute the value of x2. That is the value 0.385335. So compute the value of x3. That is unequal to 1, unequal to 2. 0.385335. It is almost like x2 and x6 are same up to the 6 digits. So this is the root. Advantage of Newton's method. Just note, I just want to tell you the note of the about the Newton's method. By Newton's method, root with high accuracy is obtained in a small number of iterations compared to other methods. In Newton's method, root with high accuracy is obtained in a small number of iterations as compared to other methods. But there is one drawback. The method converge to the root, converge to the root only for closer initial approximation. Closer initial approximation. As this method is derived whenever we take initial approximation that is closer to the root. x0 minus alpha we took is small than only Newton's method is found. So there is a limitation in Newton method that the initial approximation should be close to the root. Okay, initial approximation. this method can also be used to define the approximation of the root that are obtained by other method. Okay, so we have finished Newton method in this lecture. We'll continue with the secant method in the next lecture.